this session is going to be Eysha Shirrine Powers. Eysha Shirrine Powers is a senior software engineer at IBM Corporation. She's a cryptographic software developer with 15 years of experience in IBM Z cryptography and security. Eysha is a prominent speaker for IBM C crypto at conferences in the US and abroad and has several cryptography patents. Please join me in welcoming Eysha.
Okay, are you guys able to hear me okay? Sounds good? A little louder? I don't know, can they increase the microphone or is it okay? I just have to try to talk a little louder. Are those lights able to? At least we asked. Thank you for the introduction. So my name is Eysha Shirrine Powers. I work for IBM. What I'm going to talk to you about today is my main passion is cryptography, and so I'm a huge crypto nerd. And so we are going to go deep in the weeds on some aspects of crypto, but I'll kind of walk you through it. How many people in here already know about cryptography and security? Okay, I got about half of the hands raised. So we'll kind of walk you through the stuff that may be a little bit more complicated, but the idea is that I want everybody to kind of walk away with this session with a good understanding of, yes, data is awesome, but also that data needs to be protected. And there's significant reasons why that data should be protected, and there's different technologies that you can use to protect that data. And so this will kind of help you make decisions on what technology to use, why do you want to protect it, what are different levels of protection you might have, talk a little bit about hardware, software, and things that you can do to protect sensitive data. With all of my sessions that I've always ever presented, I do like interaction, so you guys don't have to wait until the end to ask a question. If I lose you on any particular topic, feel free to jump out, ask a question, and I'll try to clear that up or anything like that. So please feel free to ask questions as we go. I only have about 20 slides, and we have 40 minutes, and I think the next session was canceled, so we have plenty of time. So, whew. So please ask questions. Let's have a little fun, talk about crypto. And yes, I do think crypto is fun. So a little about me. So I've actually worked at IBM for about 15 years. I started off in a component called the Resource Access Control Facility, which basically grants authorization to resources and also does authentication. So if you attended this session before, you was talking about auto password. Well, also there's different means of authenticating the user ID, passwords, pass tickets, pass phrases, certificates, and things like that. And so that's all part of resource access control. I also worked on the ZOS Java crypto extension, the JCE libraries. As many of you have probably heard about JCE, it's supported on all different platforms. It's just Java. And of course, because I actually work on IBM Z, which is a mainframe system, the huge refrigerator-looking box, we actually have a unique version of JCE that works with our cryptographic hardware and our key stores and things like that are unique to ZOS and the environment that I'm in. So I worked on that team. And then I came to this team called the ZOS Integrated Cryptographic Services Facility, which is called ICSF, and I've been on that team for the last 11 years. I used to just kind of jump around from team to team. One of the nice things I like about IBM is that it's such a huge company that there's so many different opportunities that you have, and you can move around quite a bit. So in my career, it's I always stayed kind of in security, but I kind of kept hopping from team to team until I found a team that I really liked, and then I just kind of stuck with that one. So I've been on the ICSF team for 11 years now, and I've worked on so many different projects. I worked on an implementation of elliptic curve cryptography. I worked on PKCS11. It's an industry standard for crypto libraries and crypto APIs. I've worked on crypto as a service. Regional cryptographic enablement basically allows you to do crypto operations or crypto algorithms that are unique to a particular region. Imagine if you were living in China and there's Chinese unique algorithms, which are not AES or DES or the normal ones that you're used to, then you would have to have special hardware that allows you to actually do those algorithms. And so I worked on that support from an IBM perspective. I've worked on field level and cipher, crypto usage statistics, just pretty much broadly anything crypto related. It's just, to me, it's all kind of fun. I've always loved puzzles, so it's a perfect area. I actually founded an IBM crypto education community because what I found over the years in talking to different customers and clients and users of the big systems is that oftentimes our documentation could use a little bit of work. We explain it to people as if they're us, as if they're developers, and yeah, that's not necessarily a good thing because we know the code very well, other people may not. And so that community is meant to kind of help answer questions people have about how to put together the different APIs to build their own custom applications that run on ZOS. My current role, I serve as a crypto subject matter expert, so I go out to clients, and when they have questions, I talk to them. I talk to them about their systems. I talk to them about their data centers, like what Z systems they have, what storage devices they have, what coupling facilities, how they connect these different devices together, and the various technologies that they use to actually accomplish this. Because there's a lot of data. A lot of the clients that I work with tend to be like financial organizations, insurance. I work with auto, retail. Lots of big corporations are using big mainframe systems to actually like serve up their data, process their data, store their data because they're known to be very fast. I also do software development when I'm not traveling around, but my main responsibility is design and development. So actually some of these products here are things that I either wrote code for, wrote the design for, helped with testing on and things like that. And what's nice about that is it gives me a perspective of I know how it works internally, so when people ask questions about, well, why does it do this, and why does it do this, and why doesn't it work the way I want it to work, I can say, well, the reason is because, you know, we wanted to do it this way, but then there was a limitation here, a restriction here, a constraint here, and I'm able to kind of explain that to them. And then I'm also able to kind of walk them through how to use it more effectively. So it's kind of one of the benefits of being on the development side and coming up through there, and then being able to talk to people who are users. Okay, so let's get into, some background about me. I'm not from California. I'm actually originally from Chicago. I got my bachelor's at U of I. You have a question? Woohoo! Huh? Ah, nice. I got 2 in the room. That's cool. You know what's the funny thing? When I worked at IBM, I actually had to move out to Poughkeepsie, New York, and the first thing I did was I found other U of I grads with me. And so there were 3 of us who were actually in the security organization, and we thought it was the coolest thing. So I got my bachelor's at U of I got my master's degree at RPI. I have not gotten my doctorate yet. Maybe, I don't know, we'll see. Okay, so I'm gonna kind of take you through this journey where we're gonna look at the Internet of Things, and then we're gonna look at the data behind those Internet of Things, and then we're gonna look at how you can actually secure that data in the back-end systems. So IoT. So IoT, we all know, network connected devices. There are tons of them, and they are growing everywhere. What you're talking about when you think about IoT data, you're thinking about sensors. So every time, like I was in that session just like before this one on SoCal Edison, and they were talking about how they had, you know, the poles and they had the transformers, and they were going to use technology to kind of monitor things like the weather, conditions, degradation, and things like that. And I'm like, yeah, that's pretty cool. You know, I hadn't even thought about it from that perspective. I thought about the medical side, maybe smart scales. You guys might have that at home. Heart monitors, physical activity trackers, things that are kind of along those lines, but you can think, I almost apply IoT to pretty much anything. The refrigerator, you can apply it to like everybody, like a lot of people have those Ring doorbell things, and you can kind of see like who's coming to your door. It's like motion activated. So there are sensors everywhere, there are microchips everywhere, but the problem is that there's not necessarily security everywhere. It's kind of the last thing that everybody thinks about, which is a bit unfortunate. So, question. Why do we even care about security for IoT data? What do you guys think? Why do we care? Oh yeah, you do get fined. And that's actually one of the biggest drivers. What's the next biggest driver? What happened to Capital One recently? Breach, yes, that's the next one. So looking at regulations, looking at data breaches, those are the things that are pushing people to say like, you know, I really should have put security into this product just in case. And so in a way, it's a negative side, right, that there are data breaches, but on the other side, it's like kind of like lighting the fire to some of the businesses to say, hey guys, you need to make sure you're securing data. And as you guys, who I'm imagining are going to be future data scientists or future security administrators, you guys have to be those advocates to say, hey, yeah, we're collecting all this cool data, we can analyze it, but let's make sure we're encrypting it at rest. Let's make sure we're encrypting it in flight. Let's make sure we're encrypting it in our applications. So that's kind of for you guys to kind of drive that and make sure that happens. So one of these, so taking kind of this healthcare example with our IoT data, one of the big regulations in terms of healthcare is HIPAA, right? HIPAA and HiTech, which basically says that your personal health information has to be protected. Now what's interesting is that you think, personal health information, okay, I kind of know what that is. It has to be protected not only by like the organizations that are collecting it, but also by anyone that has to deal with those organizations, and we'll take a look at that too. So it's pretty interesting how it affects people, or how it affects different organizations. So, what is considered personal health information? Actually, more than you think. Now, first you might think, okay, personal health information is like, okay, who my doctor is, the last time I went, what kind of medications you took, what kind of conditions you have. That's considered personal health information. It's also considered like the provision of healthcare to someone. Which clinic did you go to? Which doctor did you see? Those kind of things can actually reveal information about your condition. Did you have a question? I'm sorry. Okay, no, it's okay. So those kind of things can actually reveal sensitive information that you have that you don't want to get out there to just anybody, right? Other things that you might also consider PHI would be your payment as well. So most people who look at payments, you have payment card industry, and traditionally whenever I talk about crypto, I usually talk about the payment side. So when I did this presentation, I specifically avoided that because I wanted to do something new and different. And so I wanted to talk about the house side. But yes, payment is very important, and that's a different regulation. You probably know, Payment Card Industry Data Security Standard, PCI DSS. That's a different regulation you have to account for. So whether you're in the health field and you're worrying about HIPAA and HiTech, whether you're in financial and you're worried about PCI DSS, you're in Europe or in the US or anywhere in the world, you're worried about GDPR. So these are some of the names of regulations and things you have to be concerned about. So could your IoT data, could it contain PHI information? Do you think? Yes, it could. And what happens if there's PHI information in that IoT data? Then it's going to be subject to those regulations. And that's why you need to secure those data. So who does HIPAA and HiTech impact? So when I first started researching this, because I work in kind of like in the crypto area, and so then you kind of start broadening and looking at like how you actually apply crypto to different fields. Payment is the usual one, but I wanted to branch out. So when you look at HIPAA and HiTech in the healthcare industry, covered entities, you would already think, okay, it has to be the health insurance company, HMOs, that kind of makes sense. Doctors, clinics, dentists, whether it's a small company, whether it's a large company, those actually apply to them too. And also the business associates which deal with that data. So if they have a transcription service or service that's backing up their data, that also counts as well, which means those providers have to protect the data just the same as all the ones that are on the left. So some of the regulations that I've mentioned, HIPAA, of course, and HiTech. PCI DSS is the one I mentioned regarding payment systems and cards. That's your credit cards. GDPR is a new one. That one was in May 25th, 2018 was the D-Day for GDPR, where essentially at that point forward, any organization that had data from any EU citizen would have to ensure that it would comply with GDPR, which means that the data had to be protected, the data had to be kept private, the data could be revoked at any time. And so what was interesting with that one is that a lot of companies thought, hey, well, that's in Europe. I don't have to care about that. I'm a US company. Well, what happens in the summertime? You get all these people that travel all over the world. They come to the US, they go back. And so what does that mean? That means in your systems, in that data that you guys have, what kind of data do you have? You have data from EU citizens as well. And so therefore, you are actually, you must adhere to GDPR just like the other European companies or corporations. Any questions so far?
Comment about the GDPR, it's a fallacy. Some American companies say, oh, we just do business in America, we don't have to apply it for that. If you ever do business with someone holding a European passport, that's all it takes.
Yep.
And like you say, they have the month of August off, and they're all over the world.
Yes. I know, it's so cool. Okay, if you haven't been to Europe or you don't have like friends in Europe, they really literally get the whole month of August off. Like everybody in France, they're like gone for like a month, and I'm just like, why can't I do that? It's so cool. I am envious of the amount of holidays and vacation that they have there. So what is the risk? And I actually heard this, I think, during your discussion as well. Famous quote, it's no longer a matter of if, but when. So what is the risk? The cost of a data breach, 2017, $3.6 million. Likelihood of a data breach, 28%. I actually would say that actually is going up. I hear about more data breaches more frequently. They seem to be increasing over time. Think about the number of records. So when you think about records, you're thinking about like pieces of data that are sitting around on somebody's computer hard drive somewhere in some storage device. 14.7 billion records have been breached. Of those records that have been breached, how many have been encrypted? 4%. That is a ridiculously low number. And the reason I think that's a ridiculously low number is because crypto is everywhere. We have crypto embedded in your phones. You have crypto in Windows. You can use Java and C. There's so many different crypto libraries that you can use to protect data. But people aren't encrypting their data. And that's kind of the downside. That's the sad point, is that they could be encrypting their data, but they're not. For me, whenever I see in the news that there's a breach, as long as I go and I read all the details and I'm just like, okay, let's see what happened. Okay, that's kind of cool. But was the data encrypted or was it clear? And when I see that it was encrypted, I'm like, yes, it's like a win for the crypto people. But when it's not, it's like, oh, come on, people. Let me help you. I'll show you how to encrypt it. Yeah. Yeah, because the cost is, there's a couple of different things you think about in terms of the cost. You think of the regulations, right? You're going to get fees and penalties when you have a breach. But think about the cost to your customers. Lost business. How many people are eager to open a Capital One account now? How many people are willing, probably want to close their Capital One account now? So they can lose business by that. Their reputation is also affected by the breach as well. Because even though it's interesting in the world of high performance computing and enterprise computing, it used to be that the biggest problem was outages. You didn't want to ever have an outage, right? That'd be like you go into an ATM and not being able to pull out your money. You'd be a little pissed. So generally speaking, outages were like this huge big deal. But outages have happened before where there's, even Facebook has had outages and things like that. You remember that. But when a company has a breach, how long do you remember that? That's a big difference. We're still talking about Target. That was what, 2014? That was 5 years ago? Home Depot? Yeah, I'm sure everybody can throw out names of breaches. Equifax, well, that was recent. That was last year. But either way, you can start to kind of see wow, these breaches actually have more significant damage to your business than an outage used to. That's a big deal. So encryption is what we're advocating. You can protect yourself using encryption. And so the goal is to kind of look at information, where that information is, and then look at different approaches that you could have to encrypt that data. So looking at the information lifecycle, so there's different aspects to that. So you have the acquisition of that data. So that's your data creation. That's when you're generating the data, copying the data. You can get it from other sources. There's when you're using that data. So that's you're reading it, you're modifying it. You can archive that data. So it's you're kind of data that you haven't used, and it's you don't want to get rid of it, but you kind of, you just want to put that to the side. It doesn't need to be right there. You can dispose of it later. When you have data that has been archived, you can always bring it back to you. So that's the nice thing about archival versus disposing the data. When you dispose it, it's gone. But when you archive it, you can bring it back if it needs to be. It's kind of I know I'm a crypto, I'm a Z nerd. It's when you migrate your data, and then you can bring it back, you can recover it. So basically what happens is you have data that you're going to access more frequently, and you have that on storage. And then when I'm not going to use it, then you're going to back it up to tape. And then it's oh, I need it again. And then you just bring it back into storage. So that way you're kind of you're always looking at capacity and resources and how you're managing those resources. And you want your resources to go where that data is going to be used more frequently. So let's look at this from an IoT perspective. So where might your IoT data reside? So we're kind of thinking about, okay, well, what are the places where we might need to protect this data? Well, of course, the physical IoT device, of course, right? That might be the starting point. And then also think about that IoT device, right? It's internet connected, TCP/IP. It's going to send data over to a provider. And so therefore, that internet packet, that should be protected too, right? Because that's where the data is going to be for a point in time. What about in memory of the application that's receiving it on the server? It could be a database. It could be some other application before it calls the database. Who knows? What about within the database itself, right? It's sitting there stored in a database. That data can be accessed by database administrators and all sorts of applications. What about the active disk or tape storage? So those are your actual, like, huge storage devices that are storing that data. That's where your data will live as well. What if you archive it? Yep, that too. And what if you have a disaster recovery backup system? One of the things we talked about before, actually, during your session is you talked about ransomware and how in Atlanta they had this big ransomware scenario where all of their data had been encrypted by this like malicious party, and then they had to well, the idea is that they would have paid the party to get the data back, but they ended up instead trying to break it and figure it out and spent more money doing that than they did paying the party. But that's another scenario. But the idea is that if they had backed up the data, right, then they would have a copy and they can bring it back online and they can make use of it. But they didn't back it up, and so they didn't have it. So what I will also pose to you, in addition to making sure you back up that data, you encrypt that data yourself, right? Because there's sensitive data there, right? So that disaster recovery system, whether it's your system or whether it's in the cloud on another provider system, that data needs to be protected there as well.
My device data goes to my phone first, and then
Yeah, okay, I'm gonna add that now to the phone. I like that. Okay, so this is a very complicated looking chart, but it's not really that complicated. I'll explain it very simply. So imagine that you're this person here, and this person here maybe has like a heart monitor. And so you have some data here in that heart monitor. So that's your IoT device. That's connected to that person or inside of that person. Now that data there has to get sent over a network, right? So it's going to be sent over some network to get to some provider. Now in my example, of course, I am a Z person, so I'm a mainframe person. And so in the mainframe environment, what you can end up having, you can have different operating systems running in what we call logical partitions. So essentially what you have is you have one mainframe, and you can bring up these different logical partitions, and each can have their own operating system. And those operating systems can be connected by something called a coupling facility, which basically is just a way of sharing resources and sending data between those different operating systems. It's very quick, very fast, very fine-tuned. And so in this environment here, you had data, came from this person here, from the heart monitor, the IoT device, went over the network, and then it went into this environment, and then maybe it's this particular ZOS image that it decided to, have the application running that would process the data. And so it processed that data here, and then it's going to write that data over the storage area network to a disk, and that's where the data is going to live. It's going to live on that disk, and whenever somebody needs it, you just read from the disk and you write it back. That gives you persistent storage of that data. So as you can see, that data has traveled through several different points before it actually got to its resting place. And so the question to you is, where do you think that data should be encrypted?
pretty much everywhere.
Yes. Pretty much everywhere. That data needs to be protected. Mm-hmm. Yeah, and that's actually a good idea too. If the data was encrypted kind of from that point of source all the way through, then that would work as well. Just have to make sure the cryptographic keys are available to all the systems that need to be able to read and write that data. So looking at encrypting data in flight. So just to kind of give you an example so you can kind of get a feel for how this encryption thing works. Network encryption is pretty cool. It allows you to encrypt data as you're sending it over some endpoint. So you're going from one endpoint to another endpoint, and you want to send the data and make sure that it's, encrypted. Now, what's interesting with network encryption, that it's only encrypted when it's like what we say on the wire. You guys know there's Wi-Fi, so it doesn't have to be a literal wire. But the data, like we say, on the wire. So it's on the wire, it's encrypted. However, like at that endpoint where the data originates, it could be in the clear. if it's in the clear when it originates, after it goes over the wire, protected, and it lands, what is it going to be? In the clear when it lands. So it's protected from anybody actually like sniffing the wire or figuring out or reading, that internet packet. But when the data lands, you have to have a different mechanism of protecting it if you hadn't protected it, from the start. So those are things to kind of think about in terms of crypto and security. So how this works is you have your person here with your heart monitor, and they will request a secure connection. And that secure connection goes to the device. They send back a server certificate. The server certificate will then say, hey, this is who I am, and it has a public key attached to it. And so the user says on this system, okay, let me validate that certificate. Are they really who they say they are? And so you have these things called certificate authority. So like if you ever go into a website and you see a little VeriSign thing, they're a certificate authority. And what they do is they validate certificates to say, hey, this person, I know who they are. This is a real certificate. This really came from them. So now at this point you say, okay, I know I'm talking to the right, the right person or the right server. And then this system here will actually generate a session key. So it just generates a symmetric key, just a set of random numbers. And then it encrypts that key with the server's public key. And so now it has his session key that it has, and then it also has this session key that's encrypted with the server's public key. And then it sends that back over to the server. And the server can get that because the server has the private key associated with the public key because they come in a pair. Now the server can actually decrypt that packet, and now the server has the same session key that the client has. And so what can they do? They can encrypt and decrypt data, send it back and forth to one another without anyone else being able to access it. Right? That kind of makes sense? So that's really what you're doing when you're, this is one mechanism or one protocol for doing encrypted data in flight. Now there's different protocols you have. I'm sure you heard of like TLS 1.2. There's actually TLS 1.3 is new. So there's all doing different protocols. And I think that one actually uses elliptic curve now. So it's kind of cool hearing about the different things that are coming. But this is just one mechanism, but you kind of get the idea is that you have some shared secret, key that you have on both sides that you have to use public key distribution in order to share the key. Any questions? Have I lost you guys so badly at this point that you're like, oh my God, I hope she just, okay. Okay, so that's encrypting data in flight. So that covers that wire when you're sending data across. But what about the data at rest? So let's say data at rest. That could be the data that's in the application in the IoT device. It could be the data that's in the database. It could be the data that's in a file, or it could be in a data set. It could be on a storage device. All those things are considered data at rest. And so how do you decide how you're going to encrypt that? Well, there's different types of encryption and different levels of encryption. So this gets to be fun for the security administrators, at least if they like crypto anyway. Because a lot of crypto people that I talk to and different users, they are all encrypting kind of at this layer here. They're doing full disk and tape encryption. You want to know why? It is. It is so easy to do. Full disk and tape encryption, and pretty much you just turn it on. And it's like just a configuration option in your, because most devices, most of the storage devices are self-encrypting devices. They're SEDs. And those self-encrypting devices, you just turn it on and it's encrypting. Boom. No work whatsoever. Key management is very easy. Everybody has it turned on. And so a lot of users that I talk to or organizations, at first they would say, yeah, I got full disk and tape. I can check this off the list. My regulators and my auditors are all happy. And so they can just go on about their merry way. And we're like, okay, that's cool, but what does that protect you against? What is disk and tape? Any idea? Any of you guys know what disk and tape encryption protects you against?
Somebody breaches your network and takes your raw disk.
Exactly. Perfect. Yes. I feel bad. If anybody hears from Capital One, we are so sorry. But yeah, so somebody actually takes the raw data. So it really is a protection against intrusion, tampering, physical removal of the data. That's what you get with disk and tape. So that means like if you have a data, imagine you have like a data center. Like you imagine these big organizations, they have full, huge buildings full of like machines and storage and all of that. And they have these, data center technicians, they come in and they manage those systems. Imagine they walk in and they're kind of disgruntled. Maybe they didn't get the pay bump that they thought that they were going to get, and they say, you know what, okay, I'm going to go and I'm going to steal some of these devices. So they can actually, they don't have to steal the big thing. They can just start stealing individual drives which contain sensitive information, and they can sell those on the dark web, right? That's sensitive information. So if you have disk and tape encryption, you cannot do that, right? Because those disk and tape are encrypted. So there's of no use to them if you're doing disk and tape encryption. However, let's imagine that you're a storage administrator and you're disgruntled and you want to steal somebody else's sensitive data. Is the data encrypted to the storage admin? No, it's in the clear. This only protects you from physical removal. So when you're actually in the system, you're logged onto the system, you're going to see that data in the clear. The key gets served to the operating system, not to individual users. So once that operating system is up, the key is served, everybody can see the data in the clear, right? Okay, so that's when you want to start looking at other levels of encryption because you're worried about other attacks. And so then you can look at encryption at like the file or the data set level. Now for those of you who are not ZOS or Z people, data set is basically just a file. It's just called a data set. But the idea is at that level, you can actually protect the data that's in a data set so that you can have someone who has access to a data set. So imagine having like someone who has read, write, read, write, execute is in the Unix world, RWX. So they have access to, that the actual, data set or the file. But then you can allow that person to like maybe delete it, to change it, and do all kinds of things to that actual data set, except they can't, you can control whether or not they can delete and manage it versus whether they can read or write to it. So there's actually a level of granularity that you don't get initially. So traditionally speaking, if you want to give someone like full authority, you kind of give them that ability to kind of like read, write, execute. So you kind of give them everything. You can kind of give that by user. But generally speaking, sometimes you want to be able to say, I want this person to be able to manage and administer this piece of data, but I don't want them to be able to see it. So imagine being in an environment where you're a storage administrator, and your storage that you're administrating, you're trying to assign this storage to this person, this storage to this person, this storage to this group, and that to that group. And by doing that, that gives you access to read social security numbers and healthcare information and credit card numbers. Should you be able to do that? No, you don't need access to that data, but you get it by default because you have to have enough authority to do a deletion or a move or a rename and things like that. And so this kind of gives you separation. So when you encrypt the data, you can actually control separately the encryption of that data and the access to the data. So it's kind of cool. Database encryption is more granular, which is really nice. You can encrypt, at the column level, you can encrypt individual fields, and it's great. Really cool thing with database encryption is it actually encrypts data in memory buffers, right? So when data is encrypted in memory buffers, that means that let's say you have a problem. You're a big organization, you have this huge Z system you just paid so much money for, and now you have some kind of issue with the database, and you have to send it to a vendor or to IBM and say, fix this for me. And so what do? You have to capture a dump or some sort of log of what happened. Well, what's in that dump? What's in that memory? Credit card numbers, payment card information, social security numbers, addresses. Yep, that's all in memory. If you do something like database encryption, or if you go one level up to application level encryption, then you're actually ensuring that the data in memory is also encrypted as well. So when someone is trying to figure out like what level of encryption to do, you want to just look at what kind of attacks are you worried about? Are you worried about memory buffers and who you send the data to? Are you worried about physical attack? Maybe, maybe not. But you just want to take into consideration that there's going to be different attacks, and you have to kind of weigh the risk and decide which level of encryption to do based on what level of risk you have. How much time do I have left? Just like checking. 11 minutes? Okay, cool. Okie dokie. So the next thing is, so we talked a little about like encryption and kind of what to think about, and the different technologies and different levels. And so one of the very basic things with encryption is, if you think about it conceptually, it's very, very simple. So to encrypt some data, all you do is you have some text that you want to encrypt, and you apply an algorithm, crypto algorithm, and you apply a key, and then you get out ciphertext. So That's really it. So you supply a key, you supply the text, you use the algorithm, and you get out some ciphertext. So that's really how that's the gist of like how it works. What's interesting with crypto is, or what's interesting with encryption, is that the algorithms are completely public. Like you can go right now, and if you wanted to know, well, what is an RSA algorithm, or what is DES, and what is triple DES, what is AES, what is elliptic curve? If you're curious about those, you can actually go, and I'm sure you can go and find the RFC, where you can actually get every detail of how that algorithm works, all the math behind it, and you could actually implement it yourself if you wanted to in your programming language of choice. All of them are out there, and they're completely public. So what that means is if they're public to you, they're also public to your attackers. So the sensitivity in your data, if your ciphertext involves data, algorithm, key, and that produces your ciphertext, then where does the security lie? In encryption. It lies with your encryption key. That's the secret piece of information, because the algorithm is public. So what needs to be secret is that key. So the key becomes the most important part of encryption. It is that thing that needs to be available at all times. It needs to be strong, and it needs to be protected. So keys. How do you go about generating these encryption keys? What's really cool about symmetric keys is that they are just random numbers. So if you ever looked at a symmetric key, then you would just see like these random like bit strings. So some sequence of like ones and zeros, or you can see it in maybe hexadecimal, or whatever format of your choice. You see it in like base 64. But either way, the idea is that it's just a sequence of bits. That's it. It has a specific length associated with it. Now you might think, okay, it has a specific length. And the reason that it has a specific length is because certain algorithms or certain operations have to occur on certain size, so what we call a block size. So like for DES, the block size is 8 bytes. For AES, the block size is 16 bytes. So it operates that many bytes at a time. So imagine if you had some piece of data that maybe is like 1,000 bytes long, and you're going to use AES or DES or any of the symmetric algorithms. When you use a block cipher, what it does is it takes that 1,000 bytes and it breaks it up into, let's say for AES, 16 byte blocks, and it encrypts 16 bytes at a time. Now, depending on the mode you use, sometimes it does that in parallel. Sometimes it has, like it does chaining, where it actually takes, the first block and it produces the output and it feeds that into the next block, and then it kind of like keeps going with all of the chains. But the idea is that you can encrypt huge amounts of data with a really small key. And that's one of the nice things with symmetric encryption. Very, very, very nice to use. And pretty much anything that's encrypting like regular data is using symmetric encryption. And symmetric basically just says that you're using the same key to encrypt that you're using to decrypt. Okay, so in terms of the key length, this actually gets pretty interesting and kind of cool. With the keys, the strongest key, so in our environment when we're like, coming up with new, encryption tools and technologies to use, we try to use the strongest keys. And so AES 256 is the one that we're using right now, which is pretty cool. However, the original was DES, and it was 56 bits long. Now, for those of you who are like math people, and you're looking at this and you're like converting like, bits to bytes, you're like, okay, so multiply by 8 and I can get, the bits. Divide by 8, I can get to the bytes. And you look at DES and it's 56 bits, and I say it's 8 bytes, and you're like, 8 times 8 is 64 the last time I checked. Hadn't changed. What's interesting with DES and that algorithm is that when it came out, originally it was 64 bits long, and then it kind of went through like validation, and one of the groups from the government went and said, hey, no, those last 8 bits, we're going to use that for parity. We're going to use that for this other thing. And so you only get 56 bits of actual security with the DES key. So it's actually like, even though what you see is going to be 8 bytes, the real security is only going to be in that first 7 bytes, so the first 56 bits. Now, what makes it interesting now is that when you think about key length, 56 bits. So a bit can have 2 values, right? It can have a value of 0 or it can have a value of 1. Those are the only 2 values it can have. And you can have 56 of those. So you have 2 raised to the 56, right? So that is the number of combinations you would have to try every possible DES key. That's what we call the key space for DES, right? Because that's the number of combinations. Because if you're going to try to break this key, you're going to try to brute force stack. It's just a random number. Just keep trying all the numbers until you get to it, right? Well, with the DES 56-bit key, that can be broken with today's computers in about 3 days. So nobody should be using DES 56-bit keys. Now imagine AES 256, and you're like, well, that's just 256 versus 56, but it's like, no, this is to the power of 2 now, right? That is significantly difficult to break and not possible to break at all with today's computers. In fact, even if you consider quantum computing, which is right around the corner, even with that, it would still, the key strength would be essentially 2 to the 128th, which is still unbreakable. So AES keys, 256-bit, is super ridiculously strong key, and we recommend using strong keys for encryption because you don't want someone to do a brute force attack to try to get to your keys, because the real security behind your data is those keys. Any questions on that? I actually, to be honest, there's so few algorithms that I would just, if I were the attacker, I'd just run through all of them. Try AES, try DES, try all the popular algorithms. There's probably, like 20? For them, that's the least of their worries, is trying the algorithms. Trying the combinations to get the key, that would be the harder part. So at least that would be the approach that I would take. I'm not an attacker, though. Any other questions on this? So encryption keys. So encryption keys, we said they have to be super strong. That's why we have these 256-bit. That's why we want to have the longer key length, because they're susceptible to brute force attack. So the other thing to consider in terms of key length, right? So we said 256, that won't be broken with today's computers. It won't be broken with quantum computers, at least not anytime soon. What does that mean for you if you lost that encryption key? Like if you accidentally deleted it or you overlaid it? What does that mean for you? That means that you will have extreme difficulty in trying to recover that key if you don't have a backup copy of it. And so key availability is also something to consider. Making sure, one, the key is strong so that an attacker can't get to it. Making sure the key is available for you because you need to be able to get to it. And I have seen several scenarios where users accidentally either deleted or overlaid their key, and they could not get that key back. Now, most cases, it was in a development environment. It wasn't in a production environment on a production system, but it is a reality. And so making sure that you have backups of your keys and you have a formal process for backing up is also important. So it's like everybody thinks that back up the data, back up the data. But like, okay, back up the data, great. Back up the keys that are protecting that data because you're gonna need those keys as well. So, avoid self-inflicted ransomware. That's essentially what you will do if you lose your key. You've essentially encrypted all your data with this key and you've lost the key, then now you can't get your data back. And so the idea is just to make sure that you think about different levels of backup, whether it's physical backups, meaning that you have data that is backed up on like a tape or a disk or some other system. A logical backup could be like, maybe you have like on your currently running system, you have a key store that has all your keys in it. And at some point in time, you're going to say, hey, I just generated 100 keys. So I'm going to go ahead and back this up so that I have those 100 keys if something should happen. Offline backup, that's when you're worried about someone hacking into your network. And so you want to make sure you protect those keys. So there's other different things that you want to consider in terms of key management. But the idea is that you want to make sure that you have a means of making sure your keys are available when you need them. How much long do I? Time? Couple? Okay. I'm almost on my last 2 slides. Things that you want to consider if you're a security person are your encryption engine. So I work on Z, so these are the huge mainframes. And what's cool with mainframe, you have like all these different PCIe I/O drawers. So you can actually have 16 crypto express adapters on the mainframes. And when you think about in terms of processing power, on the crypto express adapter, it can actually do 10,569 operations per second of AES CBC on the crypto express adapter. Now, on the processor is even faster. It's just, there's no I/O. You're just doing it on the processor itself. 327,891 operations per second. That's in a second. It's super fast in terms of the operations that you can perform. So things that you want to consider when you're thinking about which kind of encryption engine you're going to use. Think about whether or not you want a software engine or hardware. Think about the reliability, the availability, the serviceability. Think about industry certification. So if you've heard of like FIPS standards or PCI HSM or any of those kind of certifications, you want to look for those types of things. Consider performance and security. So performance is this super fast. So a lot of people use this crypto because it's super fast on the system. Versus if you were to do these operations in software, they would be much slower. Consider security. One of the features of Crypto Express adapters or also other types of adapters are that they are tamper responding. Means if someone were to try to go into your data center and they want to steal like the keys that are on these cryptographic devices and they try to open it up or tamper with it in any way, it actually destroys, I won't say it destroys itself, it clears the data. So it does what we call a zeroize. So any of the secret information that's on that Crypto Express adapter gets zeroized if you heat it up, if you try to open it, if you try to like vibrate it too much, if you shake it too much, it's gonna actually like clear all the secret information from it. Think about your memory requirements, your algorithm requirements. Do you require special algorithms or is it just the normal AES and DES and those types of things? Think about the operating system that you're running. Maybe you're running on a Linux environment, so you're going to use things like OpenCryptoKey or OpenSSL. You're going to think about APIs and libraries. Does it have to be Java? Does it have to be C? You can actually code in assembler if you wanted to. I know actually several assembler coders. I don't personally, but you could. But you have to think about those kind of things. So when you kind of get back to this big picture, there's so many different technologies that you can use to secure your IoT data all throughout its life. It's just a matter of picking and choosing those that will work for you and worrying and kind of addressing the risks that you think that you have in your organization. Now, there are different crypto technologies on the horizon, so these are just a couple of things. Crypto anchors are really cool. They're actually like super small. You can actually embed them in like a piece of rice. And the idea is that you can track things like diamonds and things like that for their life cycle. So it's an application of blockchain technology where you can actually track like, how you do kind of supply chain management. You can actually say, hey, this is where it came from, this is where it went to, and this is the consumer who received it. So you know the full life of whatever piece of information or data or unit that you're tracking. Homomorphic encryption is another cool thing. It's not ready for, it's still kind of like in process, like in research. But what's really cool with homomorphic encryption is it allows you to operate on encrypted data. So one of the things with encryption is that you encrypt the data, but then when you want to do an operation or read it, then you have to make it clear. And then you have to re-encrypt it back, right? So with this, you can actually say, here's some encrypted data, perform some operation on it, encrypt it, and you never have to worry about that data being in the clear for any moment of time, which is pretty cool. Other things, hybrid protect. So the idea is that you also want to consider encryption in the cloud as well. Another that will also lead back into Capital One as well. You can encrypt your data before it actually goes into the cloud. You can also use RESTful services to access crypto operations like crypto as a service as well. So it should be easy. Even if you don't have your own infrastructure, you can still use crypto services that are REST-based. So you can actually embed that in your applications. So that's also a recommendation. And that is it for me. Any questions? That's probably so much information.
So I was curious to get your take on this. Considering the ubiquity of these algorithms, SSL, TLS, the fact that it's been out for decades, why aren't people using it?
I think my personal opinions, and I think that there's kind of a fear around crypto and cryptography and encryption. People, unless they have someone kind of telling them they have to do it, they kind of like, okay, that just sounds complicated, I'm just going to stay away from it. I think if we can make it just as a whole simpler for people to use and simpler for people to understand, then I think that we would get more adoption of it. Because all of the tools and the capabilities are available on like every operating system, every piece of hardware. There's some type of crypto capability. It's just a matter of making it accessible or easy for people to just say, hey, you have some data, you want to encrypt it? No, you don't have to learn how AES works. You don't have to learn how DES works. You just have to know, hey, call this API, do this encryption operation. You already have a key management system set up, and then you can get that data encrypted. So I think it's not, the capability is there, the technology is there. I think that there's kind of a little bit of a fear in using encryption. That's my personal opinion.
I just comment to that. I think it was not only the fear, but it was the expense and the effort. PKI was always more complex. Shied away from it because of the
Yeah, that's a good comment. The complexity and the cost would be other factors.
I'm sorry, I think we are out of time. So thank you so much, Eysha, for that topic.